You know, every time you click a link, send an email, whatever, your data goes on this incredible invisible journey. We usually only think about the start and the finish line, right? But we almost never think about that first, most dangerous step. So today, we are diving deep into the data link layer. It's the unsung hero that makes sure your information actually survives its very first leap onto the digital highway.
I mean, really think about it for a second. What actually stops a perfectly crisp photo you send from arriving as just a scrambled mess of pixels? It all comes down to solving this one super critical problem. How do you guarantee that the data you send is the exact same data that gets received, especially on that first crucial jump between two devices?
See, sending data isn't at all like handing someone a perfectly sealed letter. It's much more like trying to shout a message across a really crowded, noisy room. The physical connection itself, whether it's a copper cable or a radio wave for Wi-Fi, is just buzzing with interference that can totally distort your message.
So, to get our data across reliably, we have to fight against three main dangers. First, the data itself can just get corrupted, plain and simple. Second, a really fast sender can completely overwhelm a slower receiver. And third, if a bunch of devices all try to talk at once on the same line, their messages just smash into each other. Let's break these down one by one. Okay, first up, data corruption. We're sending data as a series of these tiny little electrical or light pulses that represent ones and zeros. But electrical noise is literally everywhere, and it can flip those bits, turning a 1 into a 0 or a 0 into a 1, just like that.
And it's kind of crazy how fragile this whole system is. A single bit error, just one tiny little 1 accidentally becoming a 0, can change the entire meaning of a message. It can mess up a number in a bank transfer or corrupt a pixel in a photo. The consequences can actually be pretty huge.
So how in the world do we fight this? Well, the solution is this beautifully simple idea called redundancy. The whole concept is that we send some extra, non-essential bits along with our actual data. These extra bits, they act like a proofreader, giving the receiver a way to double-check if the message showed up in one piece.
So let's look at a classic trick for this. It's called a parity check. Let's say our data is 1011. If you count them up, there are 3 ones. That's an odd number. So the system just tacks on an extra 1 as a redundant bit. The new code word becomes 10111. And now look at that. There's an even number of ones. And that's the whole secret right there.
And that 5th bit is the key. It's not part of the original message at all. It's literally just there for the check. So if the receiver gets a code word and counts an odd number of ones, it knows instantly that an error happened somewhere along the way, and it can just ask for the data to be sent again. It's a simple but really powerful little security check.
Okay, so we figured out how to spot errors, which is fantastic. But a perfectly error-free message is totally useless if it arrives so fast that the receiver just can't keep up and drops it. And that brings us to challenge number 2, managing the data flood. Imagine trying to catch baseballs from a pitching machine that's just set way too fast.
This gets us to a classic networking problem, right? Your brand new, powerful laptop can send data way faster than, say, an old office printer can process it. So how do we handle this speed difference to stop the receiver's memory from overflowing and just dropping data on the floor?
The answer is something called flow control. You can think of it like the traffic light system for data. It's basically a set of rules that limits how much data the sender can blast out before it has to hit the brakes and wait for an all-clear signal, what we call an acknowledgement, from the receiver. One of the simplest ways to do this is a protocol called stop and wait, and it works, well, exactly like it sounds. The sender sends one single chunk of data, we call it a frame, and then it just stops. It won't send the next frame until it gets an acknowledgement, an ACK, from the receiver confirming that the first frame got there safely. If that ACK doesn't show up before a timer runs out, the sender just assumes something went wrong and resends the original frame. This whole process basically turns data transmission into a really polite conversation. The sender says something, then it patiently waits for the receiver to say, "Yep, got it, I'm ready for more." This puts the receiver in control, making sure it's never swamped. It's not the fastest way to do things for sure, but it is incredibly reliable.
All right, so we can detect errors and we can manage the flow. But what happens when it's not just 2 devices talking to each other? What happens when you've got a dozen computers in an office all trying to use the same Wi-Fi channel or the same physical cable?
This is where you get pure chaos. If 2 or more devices try to transmit on a shared line at the exact same time, their signals physically interfere with each other. It's the digital version of 2 people shouting into the same phone at once. The result is a collision,
and all that data just becomes a garbled, useless mess.
So the solution is basically a protocol for digital politeness. It's called CSMA, which stands for Carrier Sense Multiple Access. Let's just break that down real quick. Carrier sense means you literally listen to the line, the carrier, to see if it's busy. And multiple access just means lots of devices can use it. Put them together and you get the one core rule.
And that rule is just so simple and elegant. Listen before you talk. If the line is quiet, a device can go ahead and send its data. But if it hears someone else talking, it backs off, waits a random amount of time, and then tries again. Isn't that clever? It's a basic rule of etiquette that massively reduces the chances of a collision.
And now, for the grand finale. We've seen these different solutions for corruption, for flow control, for collisions. So how do we package all of this intelligence together into one single working unit? Well, let's take a look at the absolute workhorse of modern wired networking. Meet the Ethernet frame. This isn't just your data anymore. It's your data wrapped up in this brilliant structure that has everything it needs to navigate that first hop. It's got the address of where it's going, where it came from, and this is critical, the built-in tools to check for errors. So let's peek inside this package. You've got your destination and source addresses. That's basically the to and from on a digital envelope. You've got the data payload itself, of course. And then at the very end, you have the CRC, the cyclic redundancy check. This is like the super-powered version of our simple little parity bit. It's a sophisticated mathematical proofreader that makes absolutely sure the frame wasn't corrupted on its trip.
Seriously, every single piece of data you send over a wired network gets wrapped up in one of these frames. It's this elegant, efficient, and incredibly tough design that has totally stood the test of time, solving all those core challenges of local data travel in one neat package.
So, there you have it. The data link layer gets our data safely to the very next device in the chain. But what happens after that? Sending a message from your computer to a server on the other side of the planet involves hundreds, maybe thousands of these little hops. How does data possibly navigate that impossibly complex web? Well, that's a story for another day.